Imagine standing under the night sky filled with stars, planets, and galaxies. It's natural to wonder if there is a center to all this vastness. The question of whether the universe has a center has puzzled humans for centuries. But is there really a central point in the cosmos? This inquiry leads us to consider both the physical and philosophical aspects of the universe. If the universe is expanding, does it mean it started from a specific point? And if so, should that point be considered the center? These are the questions we will explore. To address this, we need to delve into the history of astronomy and the discoveries that have shaped our understanding. By examining the work of pioneering scientists, we can get closer to answering whether the universe has a center. Our journey begins in the early 20th century, when groundbreaking discoveries changed our perception of the cosmos. Let's start with the revolutionary work of Edwin Hubble. The 1920s were a transformative time for astronomy. Edwin Hubble, an American astronomer, made discoveries that would change the course of cosmology. Before Hubble, the universe was thought to be static and contained within our Milky Way galaxy. Hubble's observations of distant galaxies revealed something astounding. He noticed that these galaxies were moving away from us, and the farther a galaxy was, the faster it appeared to recede. This led to the formulation of Hubble's law, which states that the velocity of a galaxy is proportional to its distance from us. This discovery implied that the universe was expanding. It suggested that the universe had a beginning and was not eternal and unchanging as previously thought. Hubble's work laid the foundation for the modern understanding of cosmology. Hubble's findings raised new questions about the origin and structure of the universe. If the universe is expanding, was there a point in time when it all began? This brings us to a deeper understanding through the lens of general relativity. Albert Einstein's theory of general relativity, introduced in 1915, provides a framework for understanding the universe's expansion. General relativity describes gravity not as a force, but as a curvature of space-time caused by mass and energy. Einstein's equations allowed scientists to model the universe's behavior on a large scale. When applied to cosmology, these equations suggested that the universe could be dynamic and evolving. This was a significant departure from the static universe model. Initially, Einstein introduced a cosmological constant to keep the universe static, as he believed it should be. However, Hubble's discoveries of an expanding universe led Einstein to abandon this idea. He later referred to the cosmological constant as his biggest blunder. Einstein's contribution to our understanding of the cosmos was profound. His theory paved the way for modern cosmology and provided the mathematical tools needed to explore the universe's expansion. But to fully grasp the universe's structure, we need to delve into the Friedmann-Lemaitre-Robertson-Walker metric. The Friedmann-Lemaitre-Robertson-Walker (FLRW) metric is a solution to Einstein's field equations in general relativity. This metric describes a homogeneous and isotropic universe, which means the universe looks the same in every direction and at every point. The FLRW metric is crucial in modern cosmology because it provides a model for the expanding universe. It allows us to understand how the universe evolves over time and how its expansion affects the distance between galaxies. This metric was independently developed by Alexander Friedmann and Georges Lemaitre in the 1920s. They showed that an expanding universe could arise naturally from Einstein's equations without the need for a cosmological constant. The FLRW metric is the backbone of our current understanding of cosmology. It helps explain the dynamics of the universe and supports the concept of an expanding cosmos. But what does it mean for the universe to expand, and where did this expansion begin? Section 5. The expanding universe and the Big Bang. The concept of an expanding universe suggests that the universe was once much denser and hotter. This idea led to the development of the Big Bang theory. According to this theory, the universe began as a singularity, an infinitely small and dense point, approximately 13.8 billion years ago. The Big Bang was not an explosion in space, but rather an expansion of space itself. As the universe expanded, it cooled, allowing matter to form and eventually leading to the formation of stars, galaxies, and other cosmic structures. This expansion continues today, as evidenced by the observation of distant galaxies moving away from us. The Big Bang theory provides a comprehensive explanation for the origin and evolution of the universe. The Big Bang has profound implications for our understanding of the universe. It suggests that the universe had a specific starting point, but does this imply a center? To answer this, we need to explore the concept of no center or edge in the universe. Section 6. The concept of no center or edge. In an expanding universe, it's tempting to think of the starting point as the center. However, cosmology tells us that the universe has no center or edge. This can be a challenging concept to grasp because it goes against our everyday experiences. Imagine the universe as the surface of an inflating balloon. As the balloon expands, every point on its surface moves away from every other point. There is no central point on the balloon's surface that can be considered the center. Similarly, the universe expands uniformly in all directions, with no center. This means that from any galaxy's perspective, it appears that all other galaxies are moving away. This observation holds true regardless of the galaxy's location, reinforcing the idea that there is no central point in the universe. Understanding that the universe has no center or edge challenges our intuition, but it is a fundamental aspect of modern cosmology. To further clarify, let's use the Earth analogy to illustrate why there is no center. Section 7. The Earth analogy. To understand why the universe has no center, consider the Earth. If you travel in any direction on Earth's surface, you will eventually return to your starting point. This is because Earth is a three-dimensional sphere with no edges. Now imagine the universe as a four-dimensional sphere. Just as there is no center on Earth's surface, there is no center in the universe. Any point in the universe can be considered as central from its own perspective. This analogy helps us visualize the concept of a centerless universe. It also explains why the universe appears homogeneous and isotropic, meaning it looks the same in all directions and from all points. By understanding the Earth analogy, we can better grasp why the universe has no central point. This brings us to another critical aspect of the Big Bang. It happened everywhere simultaneously. Section 8. The Omnipresent Big Bang. One of the most intriguing aspects of the Big Bang is that it did not occur at a specific location. Instead, it happened everywhere in the universe simultaneously. This means that every point in the universe was once part of the dense singularity from which the universe expanded. As the universe expanded, all points moved away from each other. This omnipresent expansion explains why the universe appears homogeneous and isotropic. It also reinforces the concept that there is no central point from which the expansion originated. The idea of the Big Bang happening everywhere challenges our understanding of spatial relationships. It suggests that the universe's structure is not centered around a specific point, but is uniformly distributed throughout space. This omnipresent expansion has profound implications for our understanding of the cosmos. It supports the notion that the universe has no center and that every point can be considered central from its own perspective. Next, we'll explore the concept of the observable universe and its limits. The observable universe and its limits. The observable universe has limits defined by the speed of light and the age of the universe. Light from distant galaxies takes time to reach us. We can only observe galaxies within a certain distance, about 46.5 billion light-years. Beyond this limit, there may be more universe we cannot see. This highlights the vastness of the cosmos and our limited perspective. Section 10. Every observer's perspective. From any galaxy's perspective, it appears that all other galaxies are moving away. This observation is consistent regardless of where the observer is located. This phenomenon is a result of the uniform expansion of the universe. Because of this uniform expansion, every observer can consider themselves at the center of their observable universe. This subjective centrality is a fascinating aspect of cosmology and reinforces the idea that the universe has no absolute center. This perspective is both humbling and enlightening. It reminds us that our place in the universe is unique, yet shared with countless other observers throughout the cosmos. Each observer's viewpoint is equally valid in the grand scheme of the universe. Understanding that every observer can claim to be at the center of the observable universe helps us appreciate the vastness and complexity of the cosmos. It also underscores the interconnectedness of all points in the universe. Let's conclude with a reflection on our place in the cosmos. Understanding our place in the cosmos. The universe has no central point or edge. It expands uniformly, with every point moving away from every other point. The observable universe has limits, defined by the speed of light. Every observer can claim to be at the center of their observable universe. The cosmos is vast and intimately connected.